Another aspect of software safety for vehicle automation is dealing with safety of the intended function, SOTIF, and edge cases. A general approach of any safety standard is to identify and mitigate hazards. In ISO 26262, which is a conventional automotive functional safety standard, this is done using hazard and risk analysis, HARA. The idea here is to identify and mitigate risks in accordance with Automotive Safety Integrity Level requirements, ASIL requirements. This is a functional safety standard. What that means is all the faults that you deal with are inside the system. It's assumed that you know everything your system is supposed to do, meaning you have a perfect set of requirements, and that any failure of the system to perform must be due to some internal fault, for example, a hardware fault or a software defect. ISO 26262 gets you to the point where all the hazards have been mitigated, usually by invoking some sort of safety shutdown mechanism when things go wrong. That's the main idea when you have a conventional vehicle of what you need. However, once you have systems that have more advanced sensing of the external environment, you have two issues. The first issue is that it's not really possible to have a complete set of requirements. There will always be something in the real world you haven't seen before that might cause a problem. So you do not have complete requirements. The second problem is that even if your system is perfect and even if you have perfect requirements, the outside world might not cooperate in a way that lets you have perfect functionality. As a simple example, if you send out a radar pulse from a radar, that pulse might not come back if it by chance gets absorbed by something. Most of the pulses are supposed to come back, but every once in a while you'll miss one. That's not really a fault inside the system, but it's still a less than perfect operation characteristic that you need to deal with. Those types of faults are dealt with by SOTIF standards, SOTIF, safety of the intended function. ISO 21448 is an automotive SOTIF standard. Its approach to dealing with these problems is to identify and mitigate unsafe scenarios. It looks for things called triggering events, which are situations that will cause the system to fail even though there's no internal fault. The approach is to break the scenario space up into 4 regions based on whether you know what's going to happen or you don't know, and whether it's unsafe or it's safe. The known unsafe scenarios, well, those are things you already have mitigations for. Known safe, that's not a problem, it's safe. Unknown safe areas are things you don't know about, but they don't matter because they're safe. The thing that really you need to pay attention to is the unknown unsafe scenarios. These are things where there's a triggering event that will cause an unsafe result, but your system has not been designed to mitigate that problem. A SOTIF-type approach iteratively identifies problems in the unknown unsafe area and mitigates them, driving the area of that part of the space smaller and smaller to the point at which you can say the residual risk, in other words, the area of the unknown unsafes, is so small I'll still be acceptably safe at a system level, so it's okay to stop the analysis and move on with deployment. It's important when considering simulation and various risk analysis approaches to understand that this is a statistical approach to safety, but that life-critical safety requires exceedingly small failure rates. Those failure rates are beyond what is typically addressed with a statistical approach. And that stretch to get that low a residual failure rate can violate intuition that people have about statistics. For example, when doing simulations, it is common to see teams looking at key performance indicators, KPIs, to help with improving quality of the automation. KPIs can address issues such as, are all the functions working? Is the functionality actually improving when changes are made to the software? And is the fault rate decreasing? When you have a system that goes from doesn't really work very well to works pretty well, KPIs and statistical performance analysis are a great idea. Typically, if you look at statistics, 3 sigma is almost all the area under a Gaussian distribution. If you talk to manufacturing quality folks, they'll say 6 sigma is really where you want to be, that if all your parts are within 6 sigma, then you have a really high quality system. It's also known that 6 sigma requires extreme attention to quality and is a significant effort to achieve. Well, let's say you could get your KPIs to the holy grail of 6 sigma. Where does that get you? Six Sigma quality is 99.99966%. This is commonly referred to as 5 nines. That means there's 5 nines in the decimal expansion. That's certainly better than 3 sigma, and it's certainly better than doesn't really work. But it's not enough for life-critical functions. Here's an example calculation. Let's say you're building a function that is activated about every 5 feet when you drive. So this is maybe obstacle detection or lane keeping or steering or something that has to trigger many times per mile. It is almost always right, but there's some probability it'll make a mistake. In this example, let's say we have 1,000 opportunities to get something right or wrong per mile, and there's 250 million miles per fatal crash because we want to be a bit better than an unimpaired driver. And for the purposes of a Six Sigma analysis, we're going to use a 1.5 sigma shift, which is a typical number. If you put that into a sigma calculator, you get 8.34 sigma for this life-critical function. That's a lot bigger than 6 sigma and way bigger than 3 sigma. In fact, it's 11 nines. That's twice as many nines as 6 sigma quality. This means that if you thought 6 sigma was hard, you're just getting warmed up on your way to life-critical software. As a practical matter, this means that for safety, statistical approaches are often not really useful because there's so many nines there that even the slightest mistake will blow your entire failure budget. Therefore, it's common in highly critical life-critical systems to just say you have to mitigate everything you can think of because the things you did not think of are going to eat up the entirety and possibly more of all your failure budgets. It's also important to note that this entire model assumes a Gaussian distribution, which is probably the most benign distribution you can think of for this sort of thing. And unfortunately, the real world is probably even worse than this. If you think about the difference between getting something to work and getting it to work safely, one way to look at it is that getting things to work is all about what it's supposed to do. But getting things safe is really more about things it's not supposed to do that are harmful. One of the things that testers learn is that there are a lot more ways to get things wrong than there are to get things right. Those ways may be numerous, they may not happen often, and they may be really strange. But if enough of them happen often enough, then you have a problem that your system won't be safe. In other words, it's all about the edge cases, those things that are surprises. When you're talking about machine learning, some of the edge cases come from gaps in the training data and unintentional biases that are present in the training data. It's things you didn't realize that were teaching your machine learning system to do odd things it's not supposed to do. In many cases, it's unintentional, often very subtle gaming of the training data, so the machine learning system looks like it learns what you wanted, but it's probably not learning what you expected it to learn. Here's a concrete example. For safety, if you're building an automated vehicle, you want to know, is that thing I'm seeing with my camera a person? Because based on it being a person, there's certain expectations of future motion and certain safety properties you want to observe, such as a keep-away distance. Now here's the catch. Safety needs to know, is that a person? But if you ask the machine learning-based perception system, is that a person? The answer you get, you might think answers that question, but that's not what the machine learning system is going to tell you. It's answering the question, is that thing that I'm seeing with my camera like all the people already in my training data? So machine learning-based system may say, I think that's a person with a 97% probability. But it's not actually telling you if it's a person. It's telling you if it looks like all the other people it knows. The difference between those two questions becomes apparent when you think about people who are not like ordinary people, but who still might show up on a roadway. Now, to have a bit of fun and to prove how good humans are at distinguishing very subtle clues as to what they're seeing, I'm going to show a picture, and I want you, when you see the picture, to say, preferably out loud if you can, what you're looking at. And I'll give you a hint. It's either a person or a bird. So I'm going to show you a picture, and it's either a person or bird, and I want you to say the first thing that you think it is. On the count of 3. 1, 2, 3. Well, there's the picture. A machine learning-based classification system said 99.7% bird and was 99% sure there was no person there. Many people, when they see this, have an answer of bird, no wait, person, because most of the picture is about being a bird. But then when you look a little closer, you find instead of a bottom beak on the chicken, there's a woman's face, and you realize it's a person in a bird suit. Indeed, there are people in chicken suits that are out on the road, typically selling fried chicken or something like that. But the point here is that machine learning systems can be tricked by things that look pretty much like what they're expecting to see, and they're not very good at noticing subtle differences that completely change the meaning. People, on the other hand, can be initially tricked, but then revisit their result and say, wait a minute, that's not right, because there's something a little bit wrong, and they dig a little deeper and say, oh, wait a minute, I was completely wrong, and they're able to change their answers. Machine learning systems are not very good at that kind of process. In terms of edge cases, the edge cases are surprises. They're things you did not train your system on that are novel. They may correspond to a type of object you already know about, but the presentation, the way it looks or the way it acts, is not as expected, so the machine learning systems will be supremely confident that what they're seeing is, in fact, classified completely wrong. The way to look at this in terms of doing training, doing testing, doing safety is edge cases are the things you didn't think of when you were building and testing your system. They will inevitably happen to you in the real world, and the question is, what's your plan to minimize them, and what's your plan to deal with them when they actually do happen? Why are edge cases such a big deal? Well, the issue has to do with not any particular edge case, but the fact that there are so many things that are potentially edge cases depending on how you build your system. Let me give you a concrete approach to explain why these numbers can't add up and why they're such a problem. Let's do two examples for a situation in which you're going to do 1 billion miles of drive-fix drives. You're going to drive around, you're going to find problems, SOTIF triggering events, for example, things that your system doesn't do. You're going to fix the problem, you're going to keep driving, and you can do that for 1 billion miles. Now, the good news is after 1 billion miles, you should have seen most things that are going to happen, or at least intuitively after 1 billion miles, you should have seen pretty much everything. But that intuition is based on a Gaussian distribution that has very, very small tails. And it might not be true, and in fact, it's probably not true of the real world. But let's do a numeric example to illustrate the point. Let's assume that you have unsafe surprises every million miles. So your vehicle has gotten so good that something weird happens that your system does not know how to deal with only once every million miles. The question is, how many surprises are there that are out there? Well, for example, one, let's assume there's only 100 surprises or categories of surprises you've never seen before the first million miles. Each one of them is 100 million miles per surprise. So that means each one of these you'll see 10 times during testing. Revisiting that math, it's 100 million miles between each type of surprise, but there are 100 different surprises, so on average, one of them will show up every million miles, usually be a different one every time. Nonetheless, after 1 billion miles, you will have had the chance to, on average, see each of them 10 times, and if you figured that out and fixed it, at the end, you're done, no bugs left, everything's good, and you can now do your brute force campaign to prove you're safe. Well, that's a bit optimistic. Consider this picture. Is this a car or a house? Well, a little bit of both. And if you never trained on something like that, then you may miscategorize it and might do something dangerous when it starts moving at an intersection when you thought it was a house. In fact, if you go to a web search engine and type in a query such as weird road obstacles, you can get sucked into that vortex for hours of looking at all the bizarre things you'll see on the road. For those of you who decide to do the web search, welcome back. Hopefully it's still the same day, but let's continue on with the second example. The second example is still 1 million miles between unsafe surprises. But let's say there are 100,000 surprises, each one of which is exceedingly rare. Each surprise only happens every 100 billion miles. That's almost never. And you might say, well, every 100 billion miles, I'm just not going to worry about it. Well, the catch is that's only half the problem. The other half is there are so many of them that on average, there's still something is arriving every million miles. It's just, for practical purposes, always a different thing. So even if you do 1 billion miles of testing, you're only going to see 1% of the surprise population. And even if you fix everything you've only seen once, those bug fixes don't really give an improvement. You're only going to get 1.01 million miles per surprise instead of being completely fixed. Now, these are hypothetical numbers. I just took 2 points on a spectrum to do examples to explain the issue. The issue is not only how often do you see something unsafe happen that you need to fix, it's also what does the population look like? In other words, if you fix things that are a problem, if it's a huge population of problems, it will take you a long time to make progress. Fixing one problem out of 100,000 basically doesn't do anything at all. One problem out of 100, well, that's worth doing. And the question is, what does the real world look like? And the unfortunate news is, the real world probably looks more like example 2 than it does example 1. And that bodes poorly for brute force approaches to find problems and then fix them. You'll basically never get there. The distribution of the edge case arrivals matters a lot in terms of trying to understand safety. The easy, usual assumption for things arriving from the real world is that they have a random independent arrival rate, which is an exponential inter-arrival time, giving a Poisson distribution. The intuition is that there'll be some things commonly seen in testing, and most of the area under the curve, which is the cumulative probability of the arrival, will be all the way on the left, and it won't take a lot of testing to see almost everything. And the idea here is that, sure, the curve goes to infinity, but there's essentially no area under the curve at all, and at some point there's really no point looking because you've sort of seen everything. To the right, underneath that curve, are the edge cases. They're not seen in testing, but the idea is if you push the total testing time far enough, you get to the point where you've seen essentially everything, and the edge cases will arrive so infrequently that you can accept that residual risk and just not worry about it. Here's the catch. In terms of something weird showing up every once in a while, sure, maybe that makes sense. But if you look at the different types of things that might arrive, you're much more likely to find a power law distribution, which is associated with the 80-20 rule, sometimes called a heavy tail distribution or a long tail distribution. Think about it. Just because something weird arrived isn't really the issue. It's what thing arrived and how do you fix that specific thing and how long will it be before you see the next thing you've never seen before. If that's an 80-20 rule, then sure, the first 80% is easy, but the last 20% is really, really hard. If you graph a power law with the same area under the curve, you can see the entire yellow area on the left gets kicked out into the heavy tail on the right. And the issue is it never really goes to zero. There's an infinitely long curve that has that same big amount of area, but it spreads so thin it goes way, way, way far out. The issue is that if your plan is to drive around, find stuff and fix it and drive around some more, you're trying to get yourself all the way into that heavy tail, and it's going to be very difficult to do because the testing time will be very, very long to see even a reasonable fraction of all the weird things that are out in the world. As a practical matter, you're not going to be able to brute force that. You can spend as much money and time as you want looking for things in the real world, then going to a closed course to reproduce them, and then teaching your system how to handle them. But unless you have amazingly good ways of taking a single exceptional weird situation and generalizing it to a huge number of cousin weird situations, it's going to be very hard to go push your way out into that heavy tail and get to the point where you can really handle everything. Much more likely, you're going to do what humans do, which is they can handle the things they know about, but they're really good also at understanding, wait, I have no idea what's going on. I better take it easy until I figure this out, rather than being supremely confident that they have it right. Sure, humans know that on occasion, but humans are quite good at knowing when they don't know compared to machine learning-based systems. We've been talking about heavy-tailed distributions and the problems that can arise if there are a huge number of rare events that can cause life-critical consequences. But how does this relate to automated vehicle safety? Here's how it works out. The difference between driver assistance and automated driving illustrates the problem. When you have a driver assistance system, this means the human driver is in control of the vehicle, in charge of safety, and they may turn on some automation to help them drive, something like cruise control. But when the cruise control makes a mistake, it's the human's responsibility to clean up the mess, and the assumption is made that cruise control will get out of the way when the human wants to override it. If you have an active safety system, such as automatic emergency braking, the presumption is that the automatic emergency brake will not activate unless a crash is more or less inevitable. That means that if the automatic emergency brake activates and prevents a crash, it's the hero. It saved a life. If it fails to activate, well, the driver was going to hit something anyway. So really, it's the driver's fault, and the driver assistance system gets credit for saving the driver. But if it doesn't activate, well, the driver was going to crash anyway, and so even if you're imperfect, even if you're 90%, 95% proper activation, as long as you don't have false alarm activations, in other words, you have a low false positive rate, then you're the hero. This means driver assistance systems are tuned to have low false activation rates, and when they activate, they get credit. That type of situation is tailor-made for the left-hand side of a long-tail curve. It only needs to deal with the common things, and it gets credit for the common things, and something really bizarre and uncommon, if it doesn't activate, well, that was the driver's fault anyway. Let's contrast this with automated driving. In automated driving, the emphasis is not just on providing safety when it's easy and you have already seen the problem. It's on scenario completeness and coverage. The automated driving system has to do everything because the entire point of being automated is that you're not relying on the human driver to save the system if something goes wrong. That means you need sensor fusion, perception, and prediction to be essentially perfect. But what if an automated driving system is imperfect? What if you hit something out in the heavy tail that you've never seen before, the design team never saw before, the design team thought was impossible, but in fact it happens anyway? How's that treated? Well, the automated driving system's in charge of safety. So if it gets something wrong, even something that nobody ever thought of before, it's going to be blamed for the crash. In other words, it's going to be blamed for false negatives, not knowing about something out in the heavy tail, because its job is to be safe. That does not mean automated driving systems have to be perfect, but they need to be almost perfect to be able to attain the same reliability as a human driver. If an unimpaired human driver is having fatal crashes only once every 200 million miles, that means the automated driver has a lot of miles between times it's allowed to get something wrong, even if the something that happens is out in the heavy tail that it's never seen before during design, test, training, or even at a time during the system's deployment. In other words, for a driver assistance system, such as an ADAS Advanced Driver Assistance System, it gets the credit when it saves a life, and if it has a hole, well, that was the driver's fault anyway. It doesn't get the blame as long as it doesn't falsely activate and cause a crash. On the other hand, automated driving gets the blame anytime there's a crash because the whole point is there's no human to save it from making mistakes. This means that safety for automated driving will be limited by how far into the heavy tail the design and test process can push, and by how good the system is at realizing it's in a situation it's not been trained for and doing at least something that's safe, even if it doesn't know how to handle it completely. The extreme requirements to achieve safety that's simply on a par with a human driver mean that automated driving systems, ADSs, must handle unusual situations in the real world. That does not mean that they have to perform at full capability, but they need to realize that something has gone wrong that they're not designed for or that they've never seen before and react in some safe way to prevent a catastrophe. This picture of a snowstorm in North Carolina illustrates that you may have limits on how many objects are in your simulation or how many different bad things can happen at once or what kind of weather you expect in a warm southern climate. But the real world is going to do what it's going to do, and it's not going to respect those limits. So it's important that you understand that no matter what you say your operational design domain is, the real world is going to present what it wants to present. And your system needs to be able to deal with all those factors occurring, even if all that it can do in response is an in-lane stop or other safety maneuver. Beyond worrying about crazy combinations of situations and things that are obviously edge cases to a person, Don't forget that machine learning does not think the way people think. It does not reason about the outside environment. It does statistical analysis of patterns to classify objects, for example. In a famous example, a camera-based perception system decided that signs from the Burger King restaurant were really stop signs and had cars stopping at Burger King signs thinking they were stop signs. The fast food franchise exploited this with a publicity campaign. While this is a somewhat humorous example that did not result in any crashes, the point is that these systems can malfunction in ways that would have never occurred to a person because they don't actually perceive and understand the world the way humans do. Rather, they use statistical analysis that can be easily gamed if things that happen in the real world are unintentionally left out of the training data. The important takeaway here is that edge cases are not what people think should be edge cases. Rather, the characteristic that makes things an edge case has to do with anomalies, patterns, and biases in the training data that quite often would never occur to a person to worry about. So edge cases aren't things that are truly bizarre that never happen. Sometimes they're things that a person knows all about and sees on a regular basis that just happen to be missing from the training data, causing a subtle bias that can result in this case, harmless, but in some cases, potentially deadly vehicle faults. From a safety point of view, chasing down the heavy-tail objects is difficult because human intuition about the way that perception systems will fail is often not enough. Sure, some surprises are things that a normal human driver would say, "I've never seen that before. It never even occurred to me that can happen. Boy, is that weird." But some things are things humans would never consider an edge case because they know all about them because they have a robust world model and robust reasoning capability. An example that we found in a real perception system was that it had issues with clothing color. What we found was that high visibility clothing, in particular yellow, was very difficult for a camera-based system to perceive. Well, sure, it knew something was there, but it did not classify it as a person because presumably the training data had very few construction workers, and it had optimized to not worry about things that are yellow because there weren't enough examples for it to pay attention. So in this case, it got a person wrong because the person was wearing yellow, and we saw that with yellow raincoats as well. Now in this case, it might be that a LiDAR system or other system would say there's something there, don't hit it. But the meaning of someone in yellow holding, in this case, a slow stop reversible sign is subtle and extremely important to safety. And a LiDAR is not going to tell you which side of the sign you're seeing, nor infer that this must be a construction zone because there's a construction worker holding a slow stop sign. In this case, it's essential that the camera realize something's going on so that if you're in a construction zone that has just been set up and is not yet on maps, you understand at least that you've entered an unmapped construction zone and have to do something reasonable to maintain safety. Where this ends up is you will always have issues with your perception system, with your ADS, that it doesn't know what to do in some novel situation that is underrepresented in the training data. And the question is, how good is your ADS at knowing that it doesn't know what's going on instead of blindly charging ahead, supremely confident in something that is completely wrong about the outside world? Wrapping up this section, a significant change to safety for automated vehicles is the changing relevance of perception defects. Previous systems had very primitive perception, and this has changed to cameras and LiDARs and radars that are responsible for providing primary safety functions with a person perhaps not even paying attention. Getting perception right is very difficult, and we see a transition from functional safety, which is worrying about internal faults, to SOTIF and system safety, which have to do not only with internal faults, but with gaps in the system's design because it's simply never run into a situation before, and imperfections in external sensors due to noise and lost signals and dirt and weather conditions and other degradations that will inevitably happen that the system has to be able to at least recognize are impairing its ability to build an accurate model of the outside world. Ultimately, safety of these systems will be dominated by the heavy tail edge cases, Things that, despite as much testing as you can afford, are going to be things that you haven't quite seen before or some other surprise. You're going to need to push as far as you can out into the heavy tail to see everything you can reasonably see, but you need to keep a healthy skepticism as to the perfection of your engineering. There will always be things you did not think of that you will encounter, and you will likely only be acceptably safe if you at least most of the time realize, hey, wait a minute, this is something weird. I better at least do a safety shutdown instead of continuing to operate in a dangerous way without even realizing it. In other words, you need to do something safe when you encounter unknown unknowns, which will inevitably occur in the big, wide, and open real world.